Hey students, Mr. Sulik here, following up with virtual lesson number 2 on the gears and simple gear trains. So I guess in short, don't do this one unless you have simple gear trains and gears number 1 already done. So this is sort of an extension off of the first one. Just looking at some of the responses that I got in the Ed puzzle, I felt like I probably should just briefly go over a couple of the concepts that we went over in the first video. First of all, again, we're learning about gears and how they work in machines and the concepts behind how the teeth work together and how they lock in. Um, so real quick review, changing speed, the number of teeth on the driver. Remember, this is the one that supplies the power to the driven gear. These are equal size and have the same number of teeth. So the driver here has 20 teeth. The driven gear has 20 as well. Okay. So if we were to break this down into understanding, if the driver and the driven gear have the same number of teeth, they'll rotate at the same speed. So if this particular driver was going at 4.5 rotations per minute, this would go again at the same amount of speed. However, where things change is if the driven gear or the driver gears differ in size and the number of teeth. If the driven gear has fewer teeth than the driver gear, then the driven gear rotates faster than the driver gear. Okay, so again, if the driven gear has fewer teeth, so in this case, it's a much smaller object with fewer teeth, okay, then the driven gear will rotate faster, because if you were to take one full rotation here on this driver gear, this driven gear is going to rotate at a much faster speed. Okay, so if the driven gear has more teeth, so in this case, if the driven gear has smaller, and has fewer teeth, okay, then the driven gear is going to rotate much slowly than the driver gear. Okay. If we were in class today, we'd be breaking out the gear kits, and you could kind of play around with them a little bit. I will throw together probably a little bit of a hands-on lesson of some kind that'll sort of reinforce some of these things as well. Obviously, it's going to be optional at home because you don't have some of the materials at home. So let's go and talk about something called gear ratio. The ratio between the number of driver and driven gear teeth is known as the gear ratio. Okay, so the difference in the number of teeth in the driver gear, again, this is the one that supplies the power to the driven gear. This ratio here to here is what is called the gear ratio. So this driver gear, this gear has 10 teeth. This one has 20. Okay, so start to think about which one's going to be rotating faster. Think of it this way. If I were to run a sprint, I am 6'2", and I were to run a sprint against, let's say, a person like LeBron James. LeBron James is 6'9". Unbelievable athlete. Very, very fast. But he would have an advantage to begin with because he has longer legs. So for every stride length that he would have, I would have a much shorter stride length than him. I would have to make that up in order to keep up. Well, I'm really glad I'm not having to sprint against LeBron James, because I think we all know what the result of that would be. But think of it this way. I'm the driver gear. LeBron is the driven gear. Okay? I would have to get my butt moving pretty darn fast to keep up with him to begin with, because right off the bat, he has an advantage in the advantage of being taller. So for every stride length he has, I have to supply a 2-to-1 ratio. And that's how we figure this out. So again, to figure out gear ratios, I would put the number of driven gear teeth on top in the numerator and driver gear teeth in the denominator. Now, we need to reduce the fraction first before we divide. So 10 goes into 20 2 times, 10 goes into 10 once. So the gear ratio between here is the number of driven gear teeth, driven, over driver teeth. So for every one of these driven gears, okay, I'm going to have 2 driver gear teeth going. Okay, so this is going to end up having to move this much that much faster. Okay, hopefully that makes sense. Written as 2 to 1, okay, or 2. The driver gear rotates once for 2 revolutions of the driver gear. This is known as gearing down. The driven gear is slower than the driver gear. Okay, so this driven gear, okay, would be slowed down by the driver gear because the driver gear simply isn't as big. It doesn't have as many teeth. That is what's known as gear ratio. Okay. If the gears are arranged so that the driver gear has more teeth than the driven gear, this is known as gearing up. So now the difference here is that we've flip-flopped them. The big gear is here, the small gear is here. So the gear ratio can be used here as well. The number of driven gear, 10, okay, over driver gear, okay, which would be 20. So 10 over 20, reduce it down to 1 over 2, which if we convert 1 over 2 to a decimal would be 0.5. Okay, 1 to 2 or 0.5. So the driven gear rotates twice for every revolution of the driver gear. Okay, so again, the driven gear rotates twice for every revolution of the driver gear. Moving on to the next slide. Gear ratio. Example calculation. This driver gear has 8 teeth, and the driven gear has 36 teeth. So the gear ratio will be calculated as follows. The driven gear on top, the driver gear on bottom. Take a look at the ratio. So let's pick a number that will go into 36 and an 8. So 4. Around 36 divided by 4. I'm going to get 9. Okay, so let's put 9 right there. Pen out. Put 9 right there. And well, I don't need a calculator for that. 4 goes into 8 twice, but we're not done yet. Okay, so we are going to divide 9 divided by 2 equals 4.5. Okay, so it would be 4.5 over 1, or the gear ratio would be 4.5. This means the driven gear rotates once for every 4.5 rotations of the driver gear. I'll repeat that. This means that the driven gear rotates just one time for every 4.5 of the driver gear. Because this is smaller, not as many teeth, it's going to have to work that much harder, or it's going to take that much longer, rather, for the driver gear to rotate this. Okay, so 4.5 here. 4.5 turns is going to only rotate this once. Okay, so let's do a practice one together. What is the gear ratio of these gears? Okay, so let's take a look and let's figure this out mathematically. Take a moment and try to figure out what you think the answer is. Okay, what is the gear ratio of these gears? So all we have to do is 36 over 8. Oh, sorry. Switch that around. 8 over 36. I stand corrected. I have to do 8 over 36. So you do the rest on your own and figure out, of these 4 options, what is the best answer. Okay. How many of you thought it would be this one? Well, if you had followed my mistake earlier, you would have come up with this one. But we already know that this guy over here is going to have to work pretty fast because this is a large gear. So we would be able to eliminate this, and this is just incomplete work. So the best answer would be D. Let's try that again. D. All right. And again, why is that the best answer? Okay. Take 4, reduce this down. For every one of these rotations, the driven gear would rotate 4.5 times. Okay. So again, a little bit more of a review today. I will be posting the 3rd and final virtual lesson of gears and simple gear trains in the next virtual lesson. We'll also go a little bit further on some of our face-to-face lessons as well. If you have any questions, please let me know. I think there's only 2 questions in this ed puzzle. Make sure that you are keeping up. For all virtual work, I'm giving you a complete week to get it done, but do make sure that you are getting them done as well. Okay, if you have any questions, please let me know. Otherwise, until next time, see ya.